Look, first of all, thank you very much to every one of you for coming along. It can be a little bit nerve-wracking standing up on the stage in that big hall and looking out at a sea of 600 faces. It's a lot more nerve-wracking thinking that you're going to have to stand up in here and your proposal was so deadly dull that nobody's bothered to turn up to listen to it. So thank you all for being here in the first place. The title of my talk is actually a very old Fortran programmer's joke. And the other embarrassing thing that can happen for a speaker is to leave time for questions at the end, and your talk has been so deadly dull that nobody's got anything they want to ask. So I'm banking on at least one person in the room not getting the joke, so I'm not going to explain it unless somebody asks at the end. Let me introduce myself. My name is Owen. I'm one of the conference organisers. By trade, I'm a freelancer, have been for quite a number of years. Now, I've only actually been using Python seriously for 4 or 5 years, I could probably work it out, but I've been coding for a lot longer than that, and I can give you some indication of how long. Just seeing that typeface sends a shiver down my spine. That magazine was published from 1981 to 1988. Every single month that came out, you couldn't get me down the newsagent fast enough. And I picked those 2 particular editions for a couple of reasons. Firstly, I'm almost certain I owned them both. But secondly, their covers tell you everything you need to know about my history of coding. Because I learned to code on one of these, a Sinclair ZX81 machine. And yes, the storage that I used was one of these. And I'm guessing there are some in the audience where I'm going to have to say, that's what we used to call a cassette tape. I learned to code in BASIC on this machine. Actually, I learned to do a great deal of machine code on this machine because, you probably can't read it from the back, but there's a little competition running within the magazine. It says down here, win the Memotech 64K RAM for the ZX81. Now, if you had the 64K of RAM, I was insanely jealous of you. I was 11 or 12 years of age when my grandfather bought me one of these machines as a reward for passing my 11 plus. I didn't have the 64K RAM, I had the 1K that the machine came with. So anything I ever wrote had to fit in 1K of memory. So that's where I started. Can I just say that you can get Space Invaders working in 1K memory. If only I'd kept that code. But these days I'm doing a few other things, and amongst others I'm a core team member of a project called the Axelrod-Python project. Now, earlier on in this session, Vince over here gave a talk on a library that I wrote the first line of code for, and this particular library, the Axelrod-Python library, which we're going to talk about, it was Vince that wrote the very first line of code. I think Nicoletta's described this as the PYCON UK bromance. This is the project. This is the project I want to talk to you a little bit about. It's a mathematical research project in the field of game theory. It's just over 2 years old now, so it started in February 2015, and it's a project that helps us to use a game called the Iterated Prisoner's Dilemma. So I'm going to just take a minute or two to explain what on earth that is. In essence, the Iterated Prisoner's Dilemma, or IPD, is a very simple game with very simple rules, but can lead to very complex situations, which is what makes it so interesting to study. If you think of rock, paper, scissors, that's a very simple game with 2 players who have 3 simple choices to make when they play. Well, the Prisoner's Dilemma is even simpler. The Prisoner's Dilemma is even simpler. You get 2 choices, not 3. The scoring is slightly more complex, but only just. It's based on the idea that you've had a crime committed and you've got 2 prisoners sitting in a police station and they're offered a deal. They can turn evidence against their partner in crime, and in exchange for that they'll walk scot-free and their partner goes to prison for a very long time. Or they could choose to cooperate with one another. Now if they did that, they'll both go to prison, but for a far shorter length of time. So their choice is whether to cooperate with one another and reduce both their prison sentences, or whether to drop their partner in it by turning evidence against them. Now of course if they both choose to do that, they've both provided evidence against each other, and they both go to prison for a very long time. So that's why it's called the prisoner's dilemma. We can actually turn that into a very simple game, which we can represent with this grid here. Now, those of you who have been paying attention may have seen that diagram previously during the course of the weekend on a beautiful poster that was down in the lower hall at some point. So very nicely drawn by Nicoletta there. I stole her code for this slide because I was just about to work out how to do it for myself. What that grid is showing us is the two rows represent the choice that one of the players can make. They can play C or they can play D. And that means they can cooperate with one another or they can defect on one another. The two columns show the choices that the second player can make, which is also a C or a D. And when they do that, the grid shows us what score they're going to get as a result. So we've taken the idea of a lengthy prison sentence as being, that's not what you want, so that gets you a low score, and a shorter prison sentence, which is what you want, gets you a much higher score. So the scores, you want a high score in order to win the game, which is kind of the opposite way around to thinking about the prisoner's dilemma itself, but it makes for a much simpler set of rules. Now, that's not a very interesting game if you just line two players up and ask them what you're going to play, because you've got absolutely no reason whatsoever to not just simply play D against one another. Because if you play a D against one another, then you can't lose. Because your opponent is either going to play a D against you, in which case, hey, it's a draw, or they're going to play a C against you, in which case you win. So there's absolutely no incentive whatsoever for you to do anything other than play a D. But it starts to become interesting if we do something with it. If we do two things with it, actually. Firstly, we play the game over and over and over and over again. But secondly, we have more than two players. And we match them up in pairs, and we look for who wins the overall tournament of that set of players. Now that then starts to become a much more interesting problem, because if all we ever do is to play D against one another, I've just hit the wrong button, if all we ever do is to play D against one another, that's where we are here. But if we play C against one another, we cooperate with one another, neither of us wins, but there's a lot more points to share here. So if we have a pair of players that simply play D, well, neither of them's going to lose, but they're not going to get a great score either. So if two of us can decide separately that we're going to trust one another and keep playing C, well, we might not beat one another either, but we're going to get a much better score than this pair over here that just play D all the time. And what we're looking for in that case is, what's a decent strategy for winning the tournament? We may not care about winning any individual match with any individual opponent, but can we come up with a strategy that will do well in a tournament of a much larger set of players? Well, this game has been studied since around the 1950s, pretty extensively, partly because it's so simple, so with very simple rules, very complex results, extensively written about. But there was one person in particular who you may have seen a flashcard of recently. Here he is, his name's Professor Robert Axelrod. He published two papers in 1980, two very, very influential papers in 1980. He was by no means the first person to study this game. He was by no means the first person to write about it and publish. But what he was the first person to do was to say, hey, we could use computers to simulate this. That would allow us to have much greater numbers of repetitions, a much bigger set of players. It would allow us to do this easily and repeatedly and to look at a much larger set of data. And can we do anything interesting with that? His papers, particularly his second paper, have been cited over 34,000 times since publication in 1980, which says he must have found something interesting in there. So,
was it God? Is it God?
Pardon?
Is it God?
No, it isn't. Could we keep the heckling down? But what was it that he found that was so interesting? Well, to answer that question, we need to turn the clock back even further again. And in fact, to the 24th of November, 1859, and this publication here, On the Origin of the Species by Charles Darwin. So this is the theory of evolution, one of the most influential and important scientific pieces of literature ever published. But even when this was published, Darwin already knew there was a problem. He knew that it couldn't explain everything that we observe in the natural world. Although it was the best explanation that we'd come up with to date, it still wasn't complete. And in particular, what it couldn't explain was cooperative behaviour, which we see everywhere in the natural world. We ourselves, as the species at the top of the food chain, are one of the most cooperative species on the planet. But we even see cooperative behaviour between species. And how does that fit with the idea of survival of the fittest and winner takes all? Well, the answer was that nobody knew, and nobody knew for a very long time. And in truth, nobody does know now. But what Axelrod started to show for the first time in his 1980s paper was that maybe there was some evidence that cooperative behaviour could start to evolve. And he did that by running tournaments of strategies on a computer, running the iterated prisoner's dilemma. But you can do that in such a way that each round of the tournament affects the population of players in the next round of the tournament. So that if your strategy has been successful, it gets more players in the next round who are then playing that strategy. If your strategy has been less successful, you kill a few players off, and you look to study which ones have survived through to the end, which ones have thrived, which have been eaten alive, and what have we got left. And so the reason that his paper was so influential is because he started to show that there was some evidence that cooperative strategies could succeed and thrive in that sort of evolutionary modelling. And in fact, that's the logo of our project. And it's actually one of the plots that we get out of the project. In this case, we put 5 strategies into a tournament, played them against one another, and looked at the population that, as it changes over the course of the tournament. And you can see one of them in particular was very successful and swamped almost the entire population by the end. One of them just about managing to hang on and survive. We think it makes quite a nice plot, and you'll find it on a sticker of the laptop of one or two of us, and if you two think it's fascinating, we've got 1 or 2 of them to spare. Axelrod actually ran 2 tournaments and published 2 papers. His first tournament, the paper was published in March 1980, and it had 15 strategies in it. And he got those strategies by talking to colleagues, so fellow academics in half a dozen countries. And what he asked them to do was to submit a Fortran function. So he gave them the signature of the function. He said it needs to accept the following arguments, which were things like, what turn are we on? What was your opponent's last play? What was your last play? And a couple of other things. And it had to return a simple value that indicated whether that strategy wanted to play a C or a D. So a really simple signature, really simple return, and he invited a bunch of academics to submit strategies. He had 1 or 2 tucked in his back pocket that had been written about in previous papers as well. And that started to show some hints of some interesting results, so he decided he'd widen the net a little further and do it again. This time, he put invitations in. It would be lovely to be able to say, Your Computer magazine, but the paper was published in 1980, and that magazine didn't get published until 1981, so almost but not quite. He put publications in magazines that must have looked a lot like that in various countries around the world. I'm about 2 years too young to have seen it, but around about that time it was appearing in magazines like this, and he got 63 strategies coming in from all over the world, far higher number of countries took part, and a far wider diversity of contribution. One of them was from an 11-year-old in the United States. And I like to think this particular 11-year-old, who I think is probably about a year older than me, wouldn't have been sitting on a ZX81 because they were only available in the UK, but he would have been sitting at a machine with a very similar specification, reading a magazine very similar to the one that I would go to the newsagent by, and he saw an invitation and decided to take part. His strategy actually came 42nd out of the 63, which I reckon is not too shabby. And Axelrod published this paper as a result, as I said, very influential. and it's been cited thousands of times since. But he didn't publish his code, so we can't reproduce those results. So, 34,000 citations for a piece of work we're unable to reproduce. Now, I'm no academic. This was my first introduction to any kind of academic research work, and that came as a bit of a surprise. So, in 2015, Vince decided to do something about that, and the something, given that we're all sat in this room, not entirely surprising, was to create a Python library to attempt to reproduce this work and a lot of the other subsequent work that has come from it. But what then happened, as a result of getting in touch with Robert Axelrod and one or two other people, Axelrod himself to say, hey, we're going to attempt to do this, hope you don't mind, we found that actually some of his code does still exist. He had got all of the Fortran functions for the second tournament. We don't have the code for the tournament itself. We have absolutely no idea how he executed those functions. We don't know how he produced the results or how he analysed them, but we do have the Fortran code for the functions themselves. And so we thought, wouldn't it be cool if we could resurrect that code and run those functions within our library? So we thought we'd have a go at it. So let's have a look at what those look like. Don't worry, we are not going to go down this line by line, and I'm not expecting you to read it, but just for interest's sake, this is, which one is it? My notes are wrong. This is this one. Yes. This is a function that was known as K55R. The reason that I've picked it is this was the one that was written by the 11-year-old Steve Newman. So this is the code. I suspect actually his code was submitted in BASIC. We know some of these were done in BASIC and they were translated into Fortran by Axelrod's team. That's probably what happened here, I'm guessing. There wouldn't have been many 11-year-olds writing in Fortran, I guess, but we don't know. And this is the sort of thing that an 11-year-old at the time was putting together. So that's there purely for interest's sake. That's what this code looked like at that part. But this is quite a complex one, and it doesn't fit on one slide. This is actually about 3 times longer than this. So that's there for general interest, but let's move to one that we can look at. So this is a slightly different one with the exciting title of K76R. This was submitted by somebody called David Gladstein. I haven't bothered looking him up. Interestingly, this came 46th, so not quite as well as the 11-year-old, but hey. The reason I've chosen to put it here is because it fits on one slide, because it's nice and simple. And you can see the sort of thing that's going on in here. A couple of things that have caught us out left, right and centre, time and time again, when we're looking at this code. This particular line here, there's a simple conditional that says, if something is true, go to line 2. And line 2 is here. So of course, the block that immediately follows that conditional is what happens if the condition is not true, which you've only got to have spent 5 minutes using Python. That's the wrong way around. You would not believe how often we've misread these strategies simply as a result of thinking that the block after the condition is what happens if the condition is true. So that's what it looks like in its original Fortran. The other reason I've picked this one is it's one that we have actually reverse engineered and incorporated into the library itself. And that's what it looks like as a Python class in our library. I'm hoping you'll agree that's even simpler again, simply on the number of lines. The idea of meaningful variables kind of invented in the meantime as well, which makes life a lot easier. Actually, Gladstein's a pretty good example of getting as close as possible to using a meaningful variable. Fortran's limited in the number of characters that you can use in a variable name. 6 or 8, I can't remember which. Most of the authors, as far as we could tell, thought that 6 or 8 was far too profligate, and why use more than one? Which really does make life difficult. But Gladstein helped us out enormously with a meaningful variable name there. In the papers, it actually explains the meaning of Patsy as well. So we had enough here to be able to work with. And that's what it looks like in the Python library. But an interesting question arises. So we've translated the Fortran into Python and we've got it going. How do we know that our Python class is working properly? How do we know that it behaves the same way as the original Fortran function? Well, that was actually a problem way back a year or 18 months ago when we had about 30 strategies in the library. Because when the 31st gets submitted, when a pull request comes in, how do we know if it's not just the same as one we've already got? And that was already becoming a very difficult problem. Because there's no use just looking at the code. You can code up the same strategy in an infinite number of ways. How on earth can you tell whether this is just a different implementation of an identical strategy? We now have over 200 strategies in the library, and this has become a more and more difficult problem. So eventually, I stuck my hand up in the air and said, hey, I've got a clever idea of how we might do this, which was immediately shouted down by those who actually know something about the subject, but fortunately spurred them into pointing out that actually this has been written about and there are papers on this subject. And there is a technique called fingerprinting, which I'm not going to go into, largely because I don't understand it. But what it does comprise is you play a strategy against a number of probe strategies, and there are ways in which you can look at the information that's coming out of there and make pretty pictures out of it. And that really is the level of my understanding. I'm not pretending here. If you want to know anything about that, there are other people this side you can go and ask about fingerprinting. But go on, click, thank you. This is what they look like. So this is a fingerprint of actually one of the other strategies. This is the fingerprint of one of the Fortran strategies. And that's the sort of thing we get. So if we were to translate that into a Python class in our library, we can run the fingerprinting again, and we can put them side by side. Now, I picked this one because this was one of the strategies which we originally had a go at translating, and we thought we got it right. So let's have a look at what the two fingerprints look like next to one another, and there we go. And you think, great, they look similar. Yeah, but they ain't quite the same, are they? And so this was an example of where actually we had made a minor error, which if I remember correctly was to do with misunderstanding one of those conditionals, and we got it the wrong way round. And it was the fingerprint that showed us that was the case. But what we really wanted to do was to run all 63 Fortran strategies. So we've managed to translate a few of them, and we found it is hard work. Even for the really simple ones, it is hard work. The ones I've shown you are probably the more readable of the lot. Some of them, where they just use the entire alphabet with absolutely no description whatsoever. Well, anybody that wants to take it on, it's all open source, please feel free to do so, but I think we've sort of lost the will to live in doing it. So instead we thought, wouldn't it be nice if we could just execute the Fortran itself? So a few months ago, that's what we sat down and we tried to do. And of course, you can, because you can compile the Fortran into a shared object. There are many ways in which you can then talk to that from within Python. You could actually, theoretically, distribute the Fortran within our Python library itself and get the whole thing to build. We've had a go at that, it doesn't work. We've had another go at that, it still doesn't work. And I've just run out of time attempting to do it. But what we have done is compiled the Fortran into a shared object, and then we can write a simple wrapper within our library. It actually uses the C-types library, and it will call those Fortran functions and make them appear as if they were one of our classes. So we can now run Axelrod's original tournament with his original 63 strategies executing a compilation of their original code, which I have to say gives me an immense amount of satisfaction. Pretty niche satisfaction, I know, but there we go. So, what we have to ask ourselves is then, have we managed to reproduce the results? Well, let's have a look. So, we'll do a plot. There's a lot going on here, so quick explanation. The x-axis is the original rank of the strategy in Axelrod's paper. So, if you line them up in rank order in Axelrod's paper, that's what's on the x-axis. So the winning strategy is down the left-hand side, the 63rd strategy is up the right-hand side. The y-axis is what we've seen them ranked in our attempt to reproduce that strategy. We don't actually know how Axelrod determined the rank, and there are several ways of calculating it. We don't know which he used. So the reason that there are various different flavours of dot on here is because we've calculated all three, or we've calculated 3 just to see, hey, is there any difference? And so if we'd reproduced his results perfectly, oh, I've done it again, how many more times am I going to hit the wrong button? Right, if we'd reproduced his results perfectly, you'd expect to see all these dots lining up in a nice straight line along the y equals x line. And at first glance at that, you think, yay, it's pretty close. And it is pretty close. And in fact, for a lot of them, even if you look at the 3 different ways of calculating the ranking, they all end up in the same place. But, there are some really interesting outliers here. Well, let's deal with this one first, because that one was easy. When we went and poked around, actually what Axelrod had given us as what he makes available as his Fortran code isn't Fortran code at all. It's an HTML page with the Fortran in it. So the first job we had to do was to strip all the HTML tags out and get back to the code. This turned out to be, in stripping out the HTML tags, I'd stripped out one too many spaces and there was a line of code in there that wasn't being executed. Oh, hallelujah. So, in a minute I'll show you our next attempt at reproducing the results, and I'm hoping you'll spot that that one just sort of hops down somewhere closer to the line. So we thought, brilliant, a little bit of debugging, we'll find all of these. It looks like we've got a really simple set of results. But the fascinating one is this, here. And this is a strategy called Champion. It was written by a fellow called Danny Champion. It came second in Axelrod's original tournament, and he describes it at length in his paper, because it came second. So how did it come second, and how does it behave, and why did it do so well? Well, you can see there, when we ran it, the best we saw it do was about 18th or 19th, but pretty consistently around that mark as well. And we poked around at it, and we poked around at it, and we couldn't find it, we couldn't find it, and we poked around with it some more, and eventually we worked out that something wasn't quite right here, and we realised what it was. In Fortran, when you have a function, you can, if you want, specify that all the variables within that function should maintain their state for the next time the function gets called. And in fact, you can, anybody that's done any functional programming is going to recoil in horror at that idea, but you can in Fortran if you wish. What you can also do is to pass a flag to the compiler that says, even if that isn't defined, I want you to do that for all variables in the entire code base. And there was a very explicit instruction from Axelrod when he gave us this code that we must pass that flag. So all variables in all of the functions maintain their state between calls to the function. And in this particular one, we could see straight away there is no way that can work. There was a particular variable in there that needed to be reset. It was a counter. It needed to be reset to 0 every single time that strategy was matched up with a new opponent. And so we thought, well, we don't know how he ran his tournament. We don't have the code. We can't say this is a bug in Axelrod's code because we don't know what he was doing with it. But we do know it's stopping things from working properly for us. So we thought, hey, great, we fixed it. We can add a line into the original Fortran code to reset that counter, make sure that it's perfectly obvious that that's our addition, and away we go. Great, so let's have a look at the next time we ran the tournament. So, good news, this fella here has gone. I'm not quite sure which one of those it was, but it's no longer a really visible outlier. But Champion, what's going on with Champion? And the answer is, we don't know. We really don't know. At the moment, we have no clue as to why Champion is really consistently, no matter how you calculate the ranking, way off what was published in the original paper. That's our contact details. If you also find that interesting, we'd love to see you come along. If you can work out what on earth is happening with Champion, then we'd love to hear from you, because right now we don't know. If we can ever get to the point where we can reproduce the results of a paper that's been cited 34,000 times since 1980, we'd be absolutely delighted.